Hi guys, so this is 2014 question number 4. So it says train A runs back and forth on an east-west section of the railroad track. Train A's velocity measured in meters per minute is given by a differentiable function, VA, where time is measured in minutes. And selected values of VA are given in the table here. So first, we need to find the average acceleration of train A over the interval. So if you have velocity, average acceleration is the rate of change of velocity. So that's going to be part A, y2 minus y1. So v of 8 minus v of 2 over 8 minus 2. And so that equals negative 120 minus 100 over 6, so that's just negative 110 over 3 meters per minute squared. Okay, so part B says, do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some point within 5 through 8? Okay, so 5 through 8. So at t equals 5, you see the velocity is 40. At t equals 8, you see the velocity is negative 120. Now, logically, to go from 40 to negative 120, it has to pass through negative 100, right? And mathematically, what's the principle or the theorem that tells us the same thing? Well, that's the mean value theorem. So first, now we have to say, okay, is this a differentiable function? And yes, it is. Does that mean it's continuous? Yes, it is. So here's what we're going to say. We're going to first establish that VA is differentiable, which means it's continuous. So then we say, since the velocity at t equals 5 is 40, and the velocity at t equals 8 is negative 120, I'm sorry, I said mean value theorem before. It's by the intermediate value theorem, right? So therefore, by the intermediate value theorem, there is a point where v of t is equal to negative 100 over the interval 5 to 8. C. Alright, so C says, at time t equals 2, train A's position is 300 meters east of origin station, and the train is moving to the east. So it's on the positive side, moving toward the positive direction. Write an expression involving an integral that gives the position of train A in meters from the origin station at time t equals 12. And then we have to use a trapezoidal sum to approximate the position. Okay, so XA at 12, right? So the position at 12 is the position initially at t equals 2 plus the integral from 2 to 12 VA of t dt. Okay? So the initial position is 300 plus. All right, so how are we going to calculate this? This is a trapezoidal rule, right? So here for the first one, from 2 to 5, it's a t of 3, so 3 over 2 times 100 plus 40 plus another 3 over 2, negative 120 plus 40. And then the last interval goes from 8 to 12, so that's an interval of 4 over 2, negative 150 minus 120. Finally, the position at t equals 12 is negative 150 meters. All right. Part D. A second train B travels north from origin station. at time t, the velocity of train B is given by this function v of b. And at time t equals 2, the train is 400 meters north of the station. Okay. So it says to find the rate in meters per minute at which the distance between tray A and train B is changing at t equals 2. All right, so what this looks like is the following. So we have train A. It's going this way. We have train A is going to the east, train B is going north, okay? And then the distance between them is increasing. So this is origin station. They got a little creative here. Okay? All right. So this is what we have to look for. So basically what we want is, if you want to label that C, we want to know how fast C is changing. So the way to relate A, B, and C is Pythagorean theorem. And the reason we can do that is because one is going north, one is going east, so there is a right angle there. So what we want to do now is we want to take the derivative with respect to time of both sides. 2a dA dt plus 2b dB dt is equal to 2c dC dt. Okay, what we are looking for is this. Okay, so let's see what it is that we have here. We are told that when A is equal to 300, okay, so at time t equals 2, remember in the previous problem, A was, the position of A was 300, so A is 300, and now B is 400, okay, so that means Pythagorean theorem, C is equal to 500, all right? And now, so here I have 2 times 300. Well, now what about dA dt? dA dt is the rate of change of A, which is VA at t equals, when is this happening? T equals 2. So from up here at t equals 2, the velocity is 100. So times 100 plus 2b, b is 400 times dB dt. All right, so what is dB dt? That is the velocity of v. So vb at t equals 2, and we're going to use this equation for that one. So that's going to be -5 times 4 plus 60 times 2 plus 25. So that is going to be 125 is equal to 2 times c 500 dC dt. All right, and you're probably wondering why I didn't cancel out the 2's before. Could I have canceled out the 2's before? Of course you could have canceled out the 2's before. And then when you cancel out all the 2's, you get 3,000 plus, 30,000 plus 50,000 is equal to 500 dC dt. And so 80,000 is equal to 500 dC dt. And then when you divide by 500, dC dt is equal to 160 meters per minute. All right, number 5, we have an impressive chart here. Now it says the twice differentiable function f and g is defined for all real numbers x. Values of f, f prime, g, g prime are given. So first, find the x coordinate of each relative minimum of f on this interval. So for the relative minimum, right, we have to look for where f prime of x changes, right? But so let's take a look at if there is a point, a critical point here. In order to be a relative minimum, this is how the graph has to decrease and then increase. So f prime of x has to change from negative to positive. Okay, so here, all right, so let's take a look at f prime of x. Okay, so this is what this is saying. When x is -2, f prime is -5. Then until -1, f prime is negative. Then f prime is 0, then negative, then f prime is 0, then positive. So the place where f prime changes from negative to positive is at 0. I'm sorry, is at x equals 1. Okay, so we are going to say relative minimum. Okay, so x equals 1 is a relative minimum because f prime of x changes from negative to positive. The part B says, explain why there must be a value c from -1 to 1 such that f double prime of c is equal to 0. Okay, so this one here, they're very, very clever with this one. This is the mean value theorem in camouflage here, basically, right? They've camouflaged the mean value theorem. So basically we have, so what does the mean value theorem say? You have f, right? And the mean value theorem will say, so there must be a value such that f prime is equal to this. So the function and its derivative. Well, here we have f prime, and now this is saying, so there must be a point where the derivative of f prime, f double prime, is equal to a certain point. Okay, so to do that, first of all, what we have to say is f prime is differentiable. And we know by now that that means f prime is continuous. All right, so by the mean value theorem, f prime of 1 minus f prime of -1 over 2, right? From 1 to -1, it's a space of 2, is equal to 0 minus 0 over 2, which is equal to 0. So now we've established that over the interval -1 to 1, all right, in other words, the slope of the secant line is y2 minus y1 over x2 minus x1, 0. So the mean value theorem says the slope of the secant line must equal the slope of the tangent line. Oops, that was a text from Miss Kasif. All right, so that means that therefore there must be a point C such that f prime of C is equal to 0. Okay? The slope of the secant line is equal to the slope of the tangent line. The instantaneous derivative is equal to the average rate of change. Okay. C. The function h is defined by h of x is equal to ln of f of x. Okay. Find h prime of 3. Okay. Again, this is chain rule. It says to show the computations. When it says to show the computations, you want to show, more work than normal, right? Okay, so h of x is equal to ln of f of x. So basically, don't skip too many steps. Okay, h prime of x is equal to, okay, so the derivative of ln is 1 over f of x times the derivative of the inside, so that's f prime of x. So h prime of 3 then is equal to f prime of 3 over f of 3. And from the chart, f prime of 3 is 1/2. F of 3 is 7. So together, that's 1 over 14. Okay. All right, so part D. Part D reads, evaluate the derivative, the integral from -2 to 3, f prime of g of x times g prime of x. Okay, so what is this, right? Do you see how this is f prime of a function times the derivative of the inside? Right? F prime of a function times the derivative of the inside. So somebody took a derivative of this nested function, and that's what they got. Well, now the integral is telling us to take the antiderivative, to undo that derivative. Well, what is the there's a dx here. What is the antiderivative of this? Well, it's just f of g of x. Right? That's that original function, the original nested function, the derivative of which is f prime of g of x times the derivative of the inside. Isn't that clever? Props to them, right? And we're going to evaluate that from -2 to 3. So fundamental theorem of calculus, part 2, that's f of g of 3 minus f of g of -2, and so that's going to be f of, well, g of 3 is 1 minus f of g of -2 is -1, and so finally that's 2 minus 8, and that equals to -6. Okay? All right, that's just absolutely fantastic. So this is one where, there was u substitution, there was a nested function, and so on. So they could have asked you the same exact function, okay, but without chain rule, right? How would that look? So suppose you have, like a to b, f prime of x dx, right? So we know the antiderivative of this is f of x evaluated from a to b, and that's f of b minus f of a, right? We did the same thing, but, with this chain rule, u substitution, nested functions, composite functions, all of that. Okay, differential equations, everybody's favorite. dy dx is 3 minus y cosine x. Let y is equal to f of x be the particular solution to the differential equation with initial condition f of 0 is equal to 1. The function is defined for all any numbers. Okay, a portion of the slope field of the differential equation is given below. Sketch the solution curve through the point 0, 1. 0, 1. So usually, I guess they didn't do it for this because it falls on the axis, but usually they'll put a point over there. So 0, 1 is this one. And what you want to do is you sort of want to like trace, between here, right? Just that curve. I just want to see if you could follow that pattern, right? And here, be careful a little bit. It looks like it goes down a little bit, right? So following, it's going to go down quite a bit, following, right? I just sort of follow, and I go over there, okay? So that's how it looks. Okay. Does it look like it's going more down? Let's see. Let me do this here. Here we go. So just sort of follow. They're not Okay, that's good enough. I think we got the same thing. All right, so next it says write an equation for the line tangent to the solution curve in part A at the point 0, 1. Use the approximation to approximate f of 0.2. So this is linearization again. So what we need for part B is first we need the slope. So that's dy dx evaluated at 0, 1. So that's going to be 3 minus 1, that's 2. Cosine of x, that's 0. And that's equal to 2. All right, so what does the equation look like? The equation is y minus 1 is equal to 2x minus 0. So y is 2x plus 1. Okay, so y of 0.2 is 2 times 0.2 plus 1, 1.4. Okay, and last but not least, C, we want the particular solution to the differential equation with f of 0 is equal to 1. All right, we need separation of variables for this one. So dy dx equals 3 minus y cosine x. dy over 3 minus y is equal to cosine x dx. Integrating. Okay, so here I have 1 over 3 minus y. So that's going to be ln of 3 minus y, except it's u substitution, and the derivative of negative y is negative 1. So I'm just going to have a negative out here, is equal to sine of x plus c. Okay, at the initial condition, negative ln of 3 minus 1 is equal to sine of 0 plus c. So negative ln of 2 is equal to c. And that is my constant. So now, going back to the equation, negative ln 3 minus y is equal to sine of x minus ln of 2. Okay. Let's divide everything by a negative. So I have ln 3 minus y is equal to positive ln of 2 minus sine x. Okay. And so now here's what we're going to do. E to the ln 3 minus y is equal to e to the ln of 2 minus sine x. E and ln go away, so 3 minus y is equal to, okay, so here, if I have e to the a minus b, that's the same as e to the ln of 2 times e to the negative sine x. But what is e to the ln of 2? That's just 2 e to the negative sine x equals to 3 minus y in absolute values. Okay, now you have to channel your algebra 2 days, right? When you have an absolute value equation, how do you solve it? So if you have, x minus 2 is equal to 3. Do you remember how we solved it? We said x minus 2 is equal to negative 3. X minus 2 is equal to positive 3. And that's how we solved it. In short, we could have said x minus 2 is equal to plus or minus 3. So that's what we're going to do here. 3 minus y is equal to plus or minus 2e to the negative sine x. Do you guys hear those sirens? That's one of my kids' toys. I don't know what's going on. It's possessed. It's doing it on its own. All right. So negative y is equal to, oh, before I do that, I got distracted by these sirens. Okay. So now we can't have a plus or minus here, right? So let's go back to when this started. We know that f of 0 is equal to 1. So when x is 0, y is equal to 1. right? So when you go here, okay, which one of us is going to, which is it, the plus or the minus that's going to give us, you know, x is 0, y equals 1? Well, actually, it's the positive one. So this must be positive 2 to satisfy initial condition. So now 3 minus y is equal to 2 e to the negative sine x. Okay. Negative y is equal to negative 3 plus 2 e to the negative sine x. Y is equal to 3 minus 2 e to the negative sine x. And that's it. Okay, that was a doozy. I think it's definitely worth watching that screencast one more time. Okay? All right, and that was it. And we don't need to do anything else really, like no restrictions, because this is just e. The domain of e to the, you know, exponential functions is all reals. Sine x, the domain of that is all reals. So this is it. We are good to go. All right, and I will leave you here and we can connect again later.